we are talking number one, logarithm properties. This is like the properties of powers. Things you can do to mess with logarithms. Simplify, simplify. And then we're going to talk about graphing. Graphing is fairly straightforward as it is the inverse of an exponential. So if you need to, you graph the exponential and split the y and x. So, well, let's see. We're going to kind of do a little compare and contrast here. So if I have properties of powers, we've already learned those. We've been using them quite regular. What do we do with that? Simplify. Okay, they're multiplied to the exponents, right? Logarithms have a comparable property. As an example. In general, these work, they have, in the book, they have letters in them. So if I have two numbers inside a log that are multiplied, it's very similar to this one, I have a very similar result. You can split it. And they add up. So kind of, this, I think you're pretty good on this. Try to make that kind of a connection here. Most of the time, you're going to have this situation with the addition, and you're going to put it in this format to simplify it, because it's easier. So this property, we use it quite a bit. And then the sister property, this is subtraction, correct? Logarithms have a sister property to this one as well. So now let's go. Division means you can split and subtract, much like this. There isn't really a partner to this one. This is called the power property. There is no partner in this section here. So the nice thing about this is you can actually bring the two out front. Do I want to show you why that works? Yeah, it's a little involved. Okay, so we'll just avoid it and know that this works. You can take an exponent and bring it out front, or you can have a number out front and make it an exponent. We will use it both ways. It's just helpful in simplifying problems sometimes. Nothing here. And then there's one more property, equality. So I can give you that equation that means that that is true. The exponents are the same. If the bases are the same, the exponents have to be the same. That's what we're saying, right? We have a similar property for logs. If the base is the same, everything else has to be the same. If that's true, if they have the same base, we know that these have to be the same as well. You don't know what that arrow means, right? No. I can show you that.
No.
Holy cow, what's wrong? Yeah, importance implies. Okay, that's one way to think about it. So this has to happen, that means this can happen. If you're familiar with if-then statements in computer science, they're pretty big. If that is true, then this is true. That's what the arrows do. So basically, it's a directional indicator. There are others in math, we'll avoid for now, but that's what it is. Property for what? Yeah, you can't, so what it says is start here, go here. Not start here, go here. Right? Although we probably could. Okay, a couple example problems, and then we'll get to drafting and we'll be good. Let's solve some problems here. Solve for P. Yeah, that's one thing. And there are a couple ways to tackle. There's most always a couple of ways to tackle logarithms. Anybody have any ideas? Alright, yeah, that's a good attempt, because that's the property of the logs we're studying, so. Yeah, okay, you could transfer to exponential form, right? E to the 1/2. Let's get rid of that. Times 3 on both sides, right? You get your basics, your inverses. So 196. You go, let you know what the square root of 196 is. We do that, right? No, this this would be squared now. Something doesn't look right. So P would be some really large number, right? Yeah. Oh, it's 192? Oh, it is. How about that? I'm pretty sure that popped up. Okay. Let's try it the other way. This is probably where okay, so the other way would be to just write it 64 to 1/3. The cube root of 64. I think this is probably our easier method of solution. Then write it as an exponential. And we get 60 again. That's probably what the problem is. I put the 1/3 on the wrong side. For some reason, that yeah. I can't give you an answer on that one. Why does it? I'll have to think about that one. This is correct, yes. Yeah, no, this is right. I know that. The question is, how do I get from there to here? I don't have a direct answer. That's what I'm trying to say.
Wait, so, with this little, this log three forward, are you getting them step?
This?
Yeah.
That's what I'm dividing as an exponential.
But I don't know.
Yeah, like yesterday, we practiced writing these as exponentials. So, because they're inverse, remember that because logs and exponentials are inverses, we can use them to solve each other. So this always stays the base. And the 1/2 goes to the exponent and the 4 becomes, so you basically are switching these two and getting them as log. So this is a perfectly valid solution.
You don't have to do anything with log.
Because you don't have to. Right. Exactly. I'm gonna think about that one. Logs. This one is very direct use of properties of logs. Yeah, the base is the same. That's your check. Now we can set these equal to each other and solve for x. It's a basic linear. 15, 3x's. I can add one with divided. So those should be fairly straightforward for you. The next one I'm going to show you where people start to get tripped. So are kind of multiple different properties in one problem. Basically the same, right? Six. So I can multiply those two, right? So that's the direct use of our log function. Now you're going to use the same property. And you're solving a quadratic. Set it equal to 0. This one I think is factorable, yeah. Oh, no. And then what is x equal? 2 and -3. Logarithms are undefined for negative numbers. So you know on an exponential, the range is always positive, right? You graph it, it's always in the positives. Well, logs are always in the positive x's for that reason. They're inverses of x and y. So we need to check these x's, see if they actually work. If I plug -3 in, it won't work. It actually is undefined. So we cannot use -3 because logs are undefined. Well, you can shift it to the left and put it in the negatives, but a plain logarithm like this, you cannot have a negative x value in there. You can get negative answers, negative, and I'll show you in the graph and see why, but you cannot put a negative in there and get an answer. Sampling of solutions for logs. Any questions on those? Yeah, let's graph. Let's graph. This exponential. We'll compare it to its inverse. Minus 2 of the x. Do a table of values. One half. You already know that, right? You don't notice that. Okay, let's graph y equals log is 2x. It's the inverse. Geometrically, do you remember what inverse means? Reflected across the line y equals x. So if you're geometrically inclined, every point here comes over here. So we're gonna, so that's a geometric solution. We're very good across y equals x. You could also do an xy table. Now, who knows the logarithms? I don't know. I can tell you the powers of 10. Okay, I like that. The powers of 2. But graphing that's interesting. So the best way is to change it to an exponential, create your table, and flip the y and x values. Okay, so my y values were 1/2, 1, and 2. That means those are my x values. And my y values, my x's are now my y's. Let me switch the x and y. So 1/2, -1. 1, 0 now crosses the x-axis at 1. And then 2, 1 is the other one. So you can see that curve's going into the switch. I want to show you one more. Can I put it on this grid, or do you want to do one? You're okay, you're okay, you're okay. What shift does that give us? Which direction? Left, right. This family's of functions, same thing. We just shift it one to the left. Which means that -1 now becomes our intersect, and then we're going to cross and see what it is. So this one would actually, that is just shove left. This was a base 3, it doesn't change as much. And then what if I added something out here? Like, what if I put +5? Yeah, shift it up 5. It's same families of functions, you still got the same things going around your head, solve this problem. Yeah, so this the red one has an asymptote of what? X equals 0. Yeah, this one is does it have an asymptote in this direction? Sure. Shall I let you stew on it, or do you answer? Okay, here's the question. Does the exponential ever have a limit, an asymptote in this direction? You can keep going the x's, right? Also, does the log have an asymptote bound in this direction? No, it doesn't. You'll probably have to get out to like 50 million to see it come up here. But remember, we're studying the infinite there. It does not have that. So, how did you say you should? I would write something like this. The x is isolated in there. You could put 5 plus log 10. You're not looking it up. Now it's that. So there you go. All right, work down again, but you have the rest of the hour work the other 4 minutes. Happy Friday. I took number 1 off, right?
No.
There you go.
Wow, that's
That is like, the goal there would be a half an hour,
Oh, yeah, but see, I have classes.
so that is not a whole week.
It's not what we do this Saturday.
There's a whole. That's a piece, like, get on my back.
You're on my back.
He does have shop later, 8-foot 2x4. Oops. They're not coming.
Oh, sorry.
So, they're shortening 6th hour
That's it.
by 20 minutes.
Study hall. Come on. One that I care about.
Alright.
6 hours in budget.
We don't have even 60 hours.
Nope. Wrong again. So,
So do we only take it there?
subtraction. Yeah, you moved this one, so that was good. Now subtraction means you can divide these two terms. Yeah, so you have 16, right? This is 2. So you would write log base 6. 2. This would be log 30. That's just one. Log. Right, equals log 6. So that's the property. If we subtract them, you need to divide these two.